Hello. In this video, we are going to calculate the energies of the pi-conjugated system in cyclopentadiene using the Hückel method. Recall that cyclopentadiene is a 5-membered cyclic system. Using the Hückel formalism, we know that we have to solve a particular secular determinant equation which has the following terms. And we set this equal to 0. Also recall that to aid our solution, we want to make a particular assumption, and that assumption is to let x equal the quantity alpha minus the energy divided by beta. If we make that particular substitution, our secular determinant becomes the following. And we set this equal to 0. Our next step is to expand this 5 by 5 determinant using minors. Our first coefficient is going to be the x, and then it multiplies the determinant we get by removing the first row and the first column. That gives the following. For our next coefficient, we use the 1. And recall that we alternate signs so that we need a minus 1 for this particular term. And again, we get the determinant that remove the second row and the first column. The next two coefficients are zeros, so we can effectively ignore those because anything times 0 equals 0. And our last coefficient is a 1. So notice positive, negative, positive, negative, positive. So the coefficient is going to be a positive 1. And we get the determinant that we get by removing the fifth row and the first column. And now we've broken it down into a series of 4 by 4 determinants. Next, to evaluate the 4 by 4 determinants, we have to expand them as a series of 3 by 3 determinants, which gives the following terms. So again, x is going to be the first coefficient, and it multiplies the 3 by 3 determinant we get by removing the first row and the first column. And our second coefficient is going to be a minus 1 because it's the second coefficient. And we color-coded the expansion in purple because it corresponds to this 4 by 4 determinant. For the next 4 by 4 determinant, we will show that in blue. Our first coefficient is going to be a positive 1. And our second coefficient is going to be a minus 1. And then we've shown our expansion in blue. Last but not least, we need to evaluate the 4 by 4 determinant here. Our first coefficient again is going to be a 1. And our second coefficient can go across the top since we have fewer non-zero entries. And our last coefficient is going to be a minus 1 plus minus plus minus. So we have a minus 1 there. And now we have expanded the red 4 by 4 determinant as a series of red 3 by 3 determinants. Next, we can use the distributive law to distribute the coefficients in front over the terms after them. So this gives us x squared times x1, 0, 1, x, 1, 0, 1, x, minus x times the second 3 by 3 determinant, and we've showed those in purple. Now for the blue terms, you want to distribute the minus 1, so that gives us 1 times. And now a minus 1 times a minus 1 is a plus 1, so we get a plus 1 coefficient. And then, last but not least, we want to distribute the positive 1 over the coefficients for the last material here. We get plus 1 times 1, 0, 0, 1, 0, 1, x, 1. And then 1 times minus 1 is a minus 1. X, 1, 0, 1, x, 1. 0, 1, x. And recall that this is all equal to 0. Next, we expand the 3 by 3 determinants as a linear combination of 2 by 2 matrices, which gives the following terms. Our first coefficient is going to be x. Our second coefficient is a 1, it's a minus 1, because we alternate positive, negative. And then we want to do the same for the two 3 by 3 determinants in blue. Sure that we expand this one also. The only coefficient we need here is 1 because we can go across the top. And that simplifies our work a bit. Now for the blue terms, we have a minus 1. And now we want to expand along the first column, and our first coefficient is x. Our second coefficient is going to be a minus 1. Now again, for this term, so we can go across the top, and we only have one non-zero entry, and that's a 1. So that's our coefficient is going to be a positive 1. And then those are the terms that arise from the blue 3 by 3 determinants. And last but not least, we want to expand the red 3 by 3 determinants. Our coefficient is a 1. Essentially, we're going to expand across the top because we only have one non-zero entry there. Now our coefficient here is a minus 1. Our first coefficient is going to be an x. And our second coefficient is a minus 1, because we alternate positive and negative. And now we have expanded the 3 by 3 determinants in red as a series of 2 by 2 determinants. Since we can solve 2 by 2 determinants directly, we can now begin to combine terms squared x times x squared minus 1 minus x minus x times x squared minus 1. So that's the simplification for the purple terms. The blue terms equal minus x squared minus 1 minus x plus 1. And now for the terms in red, we have if we combine all those terms, what do we get? Well, we get x to the 5th power minus 5x cubed plus 5x plus 2, and this is all equal to 0. We're going to want to solve for x and then use that to determine the energies of our pi-conjugated system. We notice that the units term in our polynomial is a plus 2, so we can apply the rational roots theorem to suggest that things such as plus 2 or minus 2, plus 1 or minus 1 are possible roots of the system. So let's try minus 2 and then use a technique known as synthetic division. So our coefficients are going to be 1. Notice that we have no power x to the 4th, so we need a coefficient of 0. Our coefficient for x cubed is minus 5. We have no quadratic x squared power, so we need a coefficient of 0. The linear term is a plus 5, and our constant term is a plus 2. Again, we bring down 1. Minus 2 times 1 is minus 2. We add down the column to get a minus 2. Minus 2 times minus 2 is a plus 4. Minus 5 plus 4 is minus 1. Minus 2 times minus 1 is a plus 2. 0 plus 2 is 2. Minus 2 times 2 is minus 4. Plus 1, minus 2 times 1 is minus 2. And we get a remainder of 0, which tells us that minus 2 is a root of the polynomial. So this tells us that we can factor this particular polynomial as x plus 2. And then these are the coefficients of the remaining polynomial. That's 4th order, so we have x to the 4th minus 2x cubed minus x squared plus 2x plus 1. And we see that this is equal to 0. from the synthetic division, we get that we can factor our equation now as x plus 2 times x to the fourth minus 2x cubed minus x squared plus 2x plus 1. And we can divide this up using the properties of factors of an equation that is equal to 0, that either x plus 2 is equal to 0, or this particular quartic equation is equal to 0. In the first case, we get that x is equal to minus 2, which is what we understand already from synthetic division. But now we have the problem of trying to factor this quartic. And if we use synthetic division again, by trial and error, we will realize that there is no way to do this with integer factors. So we need a new technique in how to solve. The technique that we are going to apply is a version of completing the square. We assume that there is some quadratic equation, which we'll write as x squared plus ax plus b, and that if you square this particular expression, you will get our quartic equation of x to the fourth minus 2x cubed minus x squared plus 2x plus 1. So let's see how we might carry this operation out. So we take our quadratic equation, x squared plus ax plus b, and multiply it by x squared plus ax plus b. We're just going to use the definition of squaring. And now we can multiply term by term in a manner analogous to the multiplication of large numbers. So b times b is b squared. B times ax is abx. We'll just write it that way. B times x squared is bx squared. Now we multiply ax times b is again plus abx. And we're making sure we line up corresponding powers of x to make things easy for ourselves. Ax times ax is simply a squared x squared. Ax times x squared is going to be ax cubed. And for the final line, we have x squared times b is plus bx squared. X squared times ax is ax cubed. So we have another ax cubed here. And x squared times x squared is x to the fourth. Now we add up the corresponding powers of x. And we're left with x to the fourth. And then we have two ax cubes. So we have 2ax cubed. This is the most complicated one. So we have an a squared, a b, and a b. So that means a squared plus 2b times x squared. There abx plus abx is plus 2abx. And then plus b squared. And this looks kind of messy, but what we imagine is that with the proper choice of a and b, that this expression will be exactly equal to our quartic up here in blue. And we know that if we have two polynomials that are equal at all possible values of x, then the coefficients of x must be identical. So we compare the powers, the coefficient of the fourth power of x, the coefficients of the third power of x, and so on, to make these two expressions equal. So from the cubic powers of x, so I'll just write it as x cubed here, so we remember which power of x we're talking about. We see that 2a is equal to minus 2. So this tells us that a is equal to minus 1. Then if we look at the linear powers of x, this is x to the first power, then we have 2 times ab is equal to a positive 2. And we already know that a is equal to minus 1. So that tells us that B is equal to -1 as well. So what that means is we can factor this quartic in the following way as x squared minus x minus 1 squared. And that's equal to, let's write up here to be explicit, cubed minus x squared plus 2x plus 1. What it means is that we were able to factor this quartic now as two quadratic equations. There is no simple way to factor this quadratic, but as always we can apply the quadratic formula. And we notice that in this particular case, so now we have this equation, a is equal to +1. So we're referring to this equation now and the quadratic formula. B is equal to -1. C is equal to -1. And the important factor, b squared minus 4ac is equal to a +5. When we do that, we can write down the solutions, the values of x for this. It's going to be 1 plus or minus the square root of 5 over 2. So that tells us that the roots are, we have one set of roots, I'll put x of 1 just to show that, is equal to, plus or minus, that's 1 plus the square root of 5 over 2. And the other one, which is also a double root, I'll kind of emphasize this fact here, 1 minus the square root of 2 over 2. We can convert these for convenience and later use into a numeric value. So this particular numeric value is close to a positive 1.618. This particular value for x2 has a value of approximately 0.618. And to emphasize again, because we're solving the quadratic twice, we have a double root of x1 and a double root of x2. Since we had already found x minus 2 to be a root, we now have all 5 roots of the original quintic equation, and we are now able to write down the energies for the cyclopentadienyl anion. The lowest energy would be from the non-degenerate case when x is equal to -2. So the energy there is going to be alpha plus 2 times beta. The next highest energy, which is a doubly degenerate case, is going to be alpha plus 0.618 beta. We'll write it in terms of the decimal there. And again, alpha plus 0.618 times beta. And then the highest energy, which is doubly degenerate, is going to be alpha minus 1.618 beta. I thank you very much for your attention, and as always, have a good one.